Hello. Yeah, so it's working. Thank you. Thank you, Charles, for the intro again. And I'm back to speak about how CallStats is using AI to help decision makers build better products. So what CallStats does, for those who were not present in the first half, on the first half of my first presentation, is we are like analytics for the web real-time communication. We collect data across hundreds of apps today, mobile and desktop and browser-based. We collect across the pipeline metrics that help us measure quality of experience of end users on those calls. We leverage standards vastly, both from our background as developers and contributors to the IETF, 3GPP, W3C. I've been involved in various parts of it, including the WebRTC statistics API. When we started, our vision was very clear and simple. We noticed at the time that when real-time communication systems at that point collected data from their backends, typically to build better services, but when it came to like listening to their customers or getting data from the edge, from the endpoints, they were not very good at that. Partly because of privacy reasons and like basically either they started too quickly and were not able to collect data as a consequence of that. And what we noticed was that the way this worked for them was they would listen to feedback, then figure out what was wrong with the calls, figure out how would they fix it, and then apply a fix to those calls. And what we noticed was that we could create like a loop where we would collect data all the time, we would diagnose them in real time, and we would then be able to both fix and deploy fixes as a consequence of looking at trends and anomalies. We are integrated with most CPaaSs today with a lot of open source products and also some browsers and systems as a consequence of that. If you have a system that does not have call stats on it, more than happy to talk to you and get call stats on it. I made a joke earlier that this slide, especially this cartoon strip, has been on my slide decks from the beginning because it really very well epitomizes the reason for call stats. Because one of the things that we noticed when we started, like there was an overwhelming need or expressed by the community that for all high quality communication was all bandwidth driven, that you needed more and more bandwidth. And for real-time communications, like sometimes it was lost that you actually, the major bottleneck is latency. So latency, and for all the talks that I've heard today and yesterday, it's actually been brought up more significantly in the last few years than it had in the last decade. So this slide does a very good job, and shout out to Geek and Poke for doing this almost like 10 years ago. So I think they made this in 2009 or 10. So as I said, throughput's not the most important thing because when you look at calls and you can see that there's a latency. And if you measure latency at very fine-grained intervals, you can actually see that latency is not constant. It's all the time changing, partly because you have videos, they have frames. The frames are not all equal size. Sometimes they go into the buffer. They take a lot of time to come out of that buffer, partly because they're iframes. They get fragmented over larger packets, large number of packets. And but irrespective, what you don't expect to see is like skyscrapers like this at the end of or at the middle of a call, where the call starts and you have a skyscraper one, small one, then a blip, then a blip, and then there's a big blip that's almost 3 seconds of latency. So if you look at it from a user experience perspective, like there is a period of time, almost for this thing that's about 20, 30 seconds, there is latency is being reported for almost for 3 seconds. That means for 30 seconds, pretty much no one's able to do anything on that call. Not hearing the person, you don't know if you're speaking, you're not sure if the other party's hearing. If you're hearing, you don't know suddenly if the other party is speaking, and that leads to like just bad experience. And it causes a lot of things, problems in the media pipeline, because suddenly you have you might be getting audio and the video is being buffered. As I spoke before, one of the things that we really do sometimes is to keep audio video in sync. We try to play video faster than the audio because human psychology because we want the video to go first and then we hear the audio, partly because we've been tuned through generations that we see lightning and then we hear lightning. So like our brain is able to comprehend when we see something and then it happens on the auditory tract, we are able to like correlate it and that's fine. But if we hear something and then we see it happen later, that kind of confuses us and it frustrates us to no end. And especially even with movies and videos, if someone speaks, if you see someone speak and then you hear them speak, that's much better than the other way around. If you hear them speak and then they speak that, that's not a good experience. And this is only an audio-only call, so there is no video here. So this just shows that in this case there would be a larger, longer disruption. And I said, just coming back to my earlier talk, I talked about like what we measure. When we talk about call experience, typically we talk about the call experience, the quality of experience is the call experience when you start the call and you listen, and when you hang up, that's the. But for us, it's more the whole pipeline. So it starts from when you get into a call. So it depends on if you're on Hangouts or Zoom or something similar, where you get a URL, you get right in. The experience starts from that point on because we want to measure the page load time. We want to measure like how much time it took to set up the call. What is the context? If everyone's on the call and or not, and so on and so forth. And the call experience is measured until you get that blip at the end where it asks you either to rate the call or give feedback. And that's the most important part for us because we want to be able to correlate all the individual aspects, because if it took a long time to set up the call, it might actually already show that the call experience might not be that great during the call because it's either latencies that are causing the call to be set up slowly. So this talk is more about how we leverage AI. So one of the first things that we talk about is like bad experience. And bad experience basically means like how do we measure it and what is the trade-offs? Because experience means many things, and it's actually controlled by the user in some sense, because you're on a device, you're on a network, and you're on an application. So the application may define like what the experience will be because it controls that. But then the device and the network have also effects on how the application delivers that quality of experience to you. So for example, if you're on a bad network and it knows that you cannot do video, it might choose, the application may choose not to show you the video, right? It might just say that you're going to only do an audio call because you're not able to do this. And it might also be like the other party, right? So I'm calling someone and they're on a constrained device, for example. There's no reason for me to send like high quality video because it won't be rendered on the far side. So in those cases, I might want to do video, but I might not be able, like the application may choose not to send my video because the other party is not going to be able to render it. And so in real-time communications, it's not the same as web pages and where it's only one-to-one. You notice you have a set of capabilities on your web page, and you look at the browser or device you're in, and you decide what capabilities that the device has, and you measure them, and you say, like, this is what the experience is going to be. In real-time communications, the combinations, like, if you're calling that other person, what are the capabilities of their devices and their networks, and then the application tries to figure out what is the best it can do. So what it turns out to be is that you can't have everything, right? So like if you want high media quality, then you have to also figure out what is your device constraints. That might be CPU bound, it might be battery bound, there might be other things that affect that quality. And then there is the network aspects of it, like what are you connected to if you're on a Wi-Fi or you're on a 3G, packet losses, jitter, and so on and so forth. And typically what you want to do is you want to like get the best media quality while using the least of your device resources and the least of your network resources. And typically, this is defined. So that's what you, as application developers or service operators, that's what we want. But what happens typically is that you want it to be optimized for that situation or context. That might be defined by device or location. Like you might be in a coffee shop, and then therefore, like the public Wi-Fi in that coffee shop might not be all that great, which leads to bad quality of experience. In those cases, you might want to be able to like move that call from Wi-Fi to 3G if it exists and the user allows you to use 3G at that point, right? So do not start the call on Wi-Fi even though the person's connected on Wi-Fi because the Wi-Fi quality would be bad. So that comes down to, so I'm taking a high dimension data, like there's a tri-axis, and decomposing it into like onto a plane. So there's a leap of faith that you have to make that what we're trying to do is keep the shape of the dimensions correct, while like the relative positions might not be correct. So what it basically shows here is that you have a device which is able to do a vast media quality variation, and the network's also capable of doing that. So basically, you can do whatever you want to do in this case. You can do low quality, you can do medium quality, you can do high quality. And then there are situations where it may become like highly constrained because like the device and the network may only allow certain things, certain type of quality to appear. The good example of this is like public wireless networks, and so on and so forth, like where there might not be enough capacity or too many people, congestion in general. And there might be also situations where the device itself is not capable of doing certain things, like Android devices, which are like low to medium range in prices, not the flagship phones. So what we tried to do was initially, and this is this is something that we provide as a service to our customers, is optimal configurations. Basically, we collect data from, like we're a SaaS service, so we collect data from all the devices and all the applications that are on our service. We collect this and then we aggregate all this information we learn. And basically what we're trying to do is try to figure out what is the most optimal quality for a specific context. Now that context may be defined by either the device, by the location, by the network connectivity access, that they might be having Wi-Fi and 3G and they might be co-located. For example, right here, I have both Wi-Fi and 3G, and we are always measuring like if the call goes over Wi-Fi, what was the quality of experience? If it goes over 3G, what is the quality of experience? And if someone else comes into the same context, then with a similar device, with a similar app, we might say actually, if you prefer, it might be better to go over 3G over Wi-Fi instead of Wi-Fi because the quality of experience is better. And this is automated in a way that when the user opens the app, the application can query call stats and says like, what should I do? It gives a full configuration, says like, this is the kind of RTTs to expect, this is the kind of video quality that you should do. And that's only the beginning, because at that point we do not know who you're going to call, right? Because that's just what we know of your context in this situation. And that might actually change quickly, because you might want to call someone which is in Chicago, or might call someone in San Francisco, and we are also tracking that other person. So then we very quickly figure out like what would be the optimal quality for this communication transaction that would apply, so that you can start at the best or most optimal quality for that combination of people on that call, given the devices they're on. And that leads to situations where we start to see like trade-offs being made where it's highly media quality oriented, that you can get whatever because both the network and the devices are on good networks, or it might be device constrained and then the media quality might be lower just because the devices are not capable of doing something. So there are multiple solutions, and these trade-offs are somewhat automated today, and that's actually been a very good value proposition for customers, because what it does is that so this works in parallel to congestion control. So congestion control basically means that when you start a call, and this is what we've been doing, when you start a call, you have to start with something. And typically, you start with whatever the default you set into your code. So it might be 128 kilobits per second, or you'd say, like, I'm going to do 720p. It might be 640p, or you'd say, like, I'm going to do 4K because I know I want to do 4K all the time. Right? So you pick something as a developer, and you set it. And the second thing that you do is, so then the congestion control takes over. So it starts at that thing, and then very quickly figures out how it's going to downgrade or upgrade the quality. Because it sends a few packets back and forth, and it says like, oh, it was a really bad experience, so I'm going to like go down from 4K to 720p. And then basically the quality of experience at the beginning of the call may not be the best that's possible. And a lot of people are putting in efforts to improve the quality of experience right in the middle of the call. And then there are things that happen like walk out of the door. I'm like on a call and I walk out of the door, and today the apps are smart enough that they know that I'm walking out, my Wi-Fi signal is dropping, quickly fail over to 3G, and the call continues. Now again, that's a situation where like you cannot actually use the same kind of quality of experience or like whatever you're doing with the codec at that point when you walk out of the door is not what you should be doing when you move on to the 3G, because it might be just bad, right? And again, the congestion control would take over, and it would take a few tens of seconds before you would come in, like before it would figure out what it needs to do. And these are tools that help overcome those bridges or gaps in situations such as those. And this can easily be extended to situations where you have a 2-person call, then the 3rd person comes in, and a 4th person comes in, 5th person comes in, and you need to figure out like what is the optimal quality that would apply for all these sets of people. Some might get high quality, some might get low quality, and you need to figure out what those trade-offs are on the fly. And congestion control only works very well for moving the boundaries close to each other. If you want to like move the boundaries quicker or faster, that's not what would work for you. So this is something that is automated. The second thing that we start working on is, as I said before, as network engineers, when we started the company, we had a lot of hypotheses. We were getting a lot of data, and we were like, hey, can we see this in this data? So one of the things that I talked about in the previous thing was that from our experience, what I noticed was that whenever we had bad quality, I would turn off my video and audio and then turn that back on. And that was like an intuition that we had, because I was self-aware and I observed my own behavior, and then I said, like, if I do it, do other people do it? And we went and looked at it, right? So like we looked at the data because we have events coming in, we have like disruptions figured out, and then we were able to correlate that. But as time went on, we ran out of kind of these simple ideas that we were running into, and we needed a mechanism by which we could generate hypotheses. And coming to these events was also a good thing, because we would talk to other people and say like, hey, what are your biggest issues? What are your customers telling you? And then we would collect that and actually go and look for those things. But soon, like we are in year 4 now, so basically first 3 years we went and talked to everyone. People gave us all the simple ideas. Now people have like more complicated issues, which are always more interesting, and we go and look for them. And sometimes we don't find them. So we were like, we know there are problems out there, we just don't know what they are because people are not telling us enough. So we inverted the thing. We said like, there are a lot of people doing AI at the moment, and there's like we have data and there's machine learning. And what if we tried to like build a system that would go and look for anomalies? And one of the things that we do is we analyze data in real time, because that's what we wanted to do initially. So we built all this infrastructure from the beginning to be able to detect things in real time. And the initial reason was for notifications, because that's what people wanted. When we went and talked to people, they said, we'll buy your product if we can set a trap, right? That's what you could do with the old network monitoring systems. They said, I want to set a threshold, like if my RTT is off, if my 95 percentile RTT for like all my sessions in the last 30 minutes is over a certain, like is over 10%, is over 300 milliseconds, send me an alert. Like that's like the kind of things people wanted. And we had this thing. We have like individual connections being monitored, single conference, aggregation done at the in windows of 30 seconds, and then you have that at the app and the service. So at the end of the call, everything is aggregated and basically runs in real time. So if a call ended like 1 second ago, it shows up already. And typical notifications is what we call a point outlier, because you're looking for a point which is outlier in the last time frame has been outside whatever your expectation. So your time frame can be last 30 minutes, 1 day, week, hours, days, depending on who's looking at the data. If you're a network operational engineer, you're looking at very small time slices. You're looking at the last 30 minutes, last 6 hours. But if you're a product manager or if you're a CXO or similar, you're looking at larger, because you've delegated all the small issues, like the issues that are very urgent to people. But then what you want to measure is like, how is the product doing over a period of time, like over the last 30 days, over the last 15 days? What are the emergent issues, so that engineering and the company can focus on those bigger things as an OKR or operational key target over a period. So basically, if you look at a point outlier, it's like this. You have a threshold, you have a metric, you have a notification. And that notification can go today to pagerduty, can go to SMS, can be a phone call, can go to Slack, wherever like your ops people are. And then the metrics might be load, CPU, round trip times, failures, depending on what you're measuring. So if you're measuring performance of your infrastructure, then those are the notifications that you're looking for. If you're a developer and you just rolled out your latest congestion control algorithm, you want to know how that congestion control algorithm is performing vis-a-vis the old versions. And then you set thresholds like you want to. So one of the things that a good example of this would be like an RTT. Like you see this and you basically get this over days. So you can see like there might be alerts going out, at the beginning of the weeks. Every once in a while when the threshold of 300 milliseconds is breached, so you might get 40 notifications over a period of month, 40 to 500, depending on how many times that thing went up. And you can see like it goes down and up. So someone who's building products has to take a step back and see actually like what does this notifications, are we fighting fires or do we have like the whole forest on fire, right? So what is it that we're doing? And people who are in operations are fighting fires every day. So then we came up with ideas like contextual outliers. So you can't have point outliers, then you want contextual outliers, and they might be situations, right? There's Thanksgiving coming, there is Christmas, there are situations like weekends. Weekends are different for different parts of the world. We have customers in Israel and the Middle East, their weekends are different from what we thought the weekends are, and so on and so forth. So the systems suddenly need to become contextually aware to figure out like whatever you learned for, let's say, for the rest of the world does not apply for that part of the world because their weekends are slightly different. So if don't send an alert, like for example, you could build an alert where you say like, hey, my traffic is lower on the weekends, so my threshold should be kind of different, right? And like you could express that as a network engineer, but if your app is globally deployed, how do you do that? Like how do you understand where your users are and how those alerts should work for those contexts? So you need something that could help without defining these explicit identifiers, because you want what we typically want with notifications, do what I mean, not what I said. But how we express a notification or a trap is explicitly, right? We say, this is what I want it to do. So it's not what I mean, it's what I'm telling you to do is what you will do. So like you need this ambiguity, and actually AI allows that ambiguity to exist because it can learn these things. It can say like, oh, these kind of calls in this area are different from like the other parts of the world. And it can figure out these clusters without explicitly telling it. And then there are things that are collective outliers. So one of the things that we noticed is notification suppression. When things go wrong, they go horrendously wrong. So there are like hundreds of notifications coming, and you actually get like 400 notifications. And then it basically becomes like the network operator or the operational engineer has to go through all these and figure out which one is the most important one. Because you have the RTTs flying, you have failures flying. You do not know if your RTTs are bad because the failures are happening, or is there a outage? So you start with like taking a step back and you say like, let's start with the simple things first and see like, are the servers alive? Are servers all available? And then you walk through this decision tree when you're getting these notifications, which is really bad because the notification should have already figured this out, right? Because something's notifying you, and why is it notifying you and then making you do all the hard work when it already knows what it should be telling you about? So what we did was we basically took all these things together. So there are three parts of our anomaly detection system, and we are actually rephrasing some of the terms because when people talk about anomalies, they talk about anomalies as a single thing. But what for us anomalies mean is like a more overarching term, and it basically means that we're detecting trends. We're looking at deviations, which is what anomalies actually mean, and fluctuations. And we're looking at these things at various time ranges. So we're looking at it in short time ranges like 30 minutes, 30 seconds, 30 minutes, 3 hours, 1 day, 1 week, 1 month, 3 months. So basically we're collecting this data and we're trying to aggregate these over larger time frames so that we can drill in and drill out very quickly by looking at the trends and deviations over short and larger time frames, and also look at these fluctuations and deviations as a consequence of each other. So basically, we have a system which detects these things, which are basically statistical and linear algebraic, but then all these things feed into an AI system, which is trying to figure out like what is happening. And the good thing is that we're kind of passing on some of that responsibility back to the customer or our end user in some way by like throwing notifications. And basically, I would not look at the what the notification is saying, but look at the two things that we're offering them. We offer them two choices. One is discover more or remind me later. And that shows us urgency, right? So basically, we're learning over time, like what these features that the notification that we're showing them, which of these are urgent and we learn that, and that feeds back into the AI to say, like, this is something that is interesting, but and they can dismiss it, right? They can also say, do not show this message again. So the third one is like, I don't care about it ever. So that also gives us feedback on like what's interesting and what's not. And so we're using all these three components to like figure out if the notifications that are showing are important or not, and learn as a consequence of that. And then we can learn across services to see like, hey, this was an urgent message that we showed. Like a similar message was shown to another operator, and they dismissed it. We can also show it again and see if they dismiss it. And if they dismiss it, we start to see trends across applications that we know that are not interesting anymore for this class of service providers, for example. So before we built something like this, we had something called automatic diagnosis. One of the things that I learned very quickly was that when we build a product and I would talk to customers, they would just want to talk to me. They were like, hey, we give you the data. Can we like have professional services where we talk to Varun? Right? Because you go and look into the calls, I would get on, because as a process of selling the product, we would talk about like, here, we got this data. These are the problems that we're seeing in your data. And they're like, that's cool. Like, their engineers would be on the call and they say, like, this is awesome because now you're telling me what we should be doing as opposed to my engineers going and looking at it. So basically, what it shows is that what we did was we took the data and we converted it into statements so that their engineers would not need me to figure that out. So we basically ran analysis on the call. We figured out what's wrong with the call, and we would say, like, hey, this person joined the call 4 times. Please investigate. His RTT was high. Please investigate, and so on and so forth. So basically, we came down to using assisted decision-making for looking at past performance for their device, looking at active measurements. We run active measurements before the call. We run active measurements after the call. And as I said, there was notifications on the RTT, and I showed you an RTT earlier, which was almost flat, and it was going over 300 milliseconds. But the AI was able to figure out a lot of things by itself. So it was basically able to see geographical locations and see that the fact that North America, it increased from 100 to 200 milliseconds and then increased from 200 to 300 milliseconds in the same period, and was not the cause of the high RTTs that we were seeing there. So what we saw before was that all the average RTTs were above 200 milliseconds. And here you can see like North America was not affected, so no notification need to go out for this. The same thing for Europe. It's also seeing a trend increase from 100 to 200 to 250 and then 300 to 400. So when it generated that message, it had already seen not only the larger trends, but also the area located trends, like geographical trends for it. And why was it interesting? Because the most important thing that we noticed was the objective quality, the quality of experience was actually varying by geographies. So for people who were on the same continent, the quality was very good. For people who were not on the same continent, where the calls were going across the internet, across continents, it was bad. So I'll leave you with our last 2 slides. What did we learn? We learned like what configurations work for an endpoint, specifically for that device in a particular context. Second thing we learned was what routes are performant. Like we learned like some continental routes are better performing than other continental routes. Which we also realized that when applications not peer-to-peer and they use a server-assisted infrastructure, what servers are performing better. And lastly, when and how the traffic is affected, basically quality of experience. And what we're trying to move towards is like we now have a wealth of data, we have wealth of notifications, we're able to suppress notifications intuitively to things that people can then like basically do a root cause analysis. So you get a notification, then you can see like here are the 4 things that we are seeing that caused this notification to be generated. You can look at these 4 notifications independently, or you can see them together. And what we want to move towards is like self-driving networks, because these notifications can be consumed by humans, but can also be consumed by machines. And if they're consumed by machines, the machines can make decisions as a consequence of taking that and saying like, hey, I can start more servers, or I can do these new things, move my servers closer to the end users, closer to the edge, or move them further to optimize for either quality of experience vis-a-vis the CapEx or OpEx that they're trying to optimize for. And we can do it at the ends, and we can do it in the middle. So overall, this is my last slide. We like to close the loop. We're detecting, we're diagnosing, and we're deploying, and we want to, like, we're measuring, we're inferring, and like the last piece of the puzzle is control. And we're like, what we're trying to figure out is what that control surface can be. Is it notifications where humans would consume it, or can we take it one step further and like pipe it into software-defined networks, network function virtualizations, and so on and so forth, the trends that we're seeing in the larger infrastructure space. Thank you. I'm happy to take questions.
Have you ever run into scenarios where an operator of a service has been willing to let you go in and change their infrastructure in order to,
Yeah, so the ones that are not on a platform as a service, so there are a lot of customers on CPaaSs where they don't control the infrastructure either. So then they use these notifications. That's why these notifications are textual, partly because they take this and then they go back to the CPaaS vendor and say, like, this is what CallStats is telling us. Can you investigate it with us? And this is what they have shown, that they're showing the quality of experience really bad. That is not the answer to your question, but the second is people who do control the infrastructure are able to use these notifications to add new conferencing bridges, for example. And for them, this is something that if they already are in a location, they can use the notification. Some of them are using the notification to scale out and scale in. But when it tells them, like, hey, you have to start a new infrastructure in Singapore, or like basically in Asia, your infrastructure sucks, then you need to like start something, that's more human controlled. And that's still something that we're investigating, like how do you do that for things that are on Amazon, for example, because that does require you to go and make an initial investment by turning on servers and like buying the EC2 instances or similar. And so that's still an open issue. But we are more than happy to partner with people, especially equipment vendors, and figure out like if they can consume it and how do they see this scale out happen.
So some of the stuff that you listed as probably anomalies, at least, depending on how you define anomalies, at least to me, were more along the lines of anticipatory traffic.
Right.
For those, traditional networks have just dimensioned on those days, and that's not an anomaly. What becomes an anomaly really is surges of traffic where you do not know if the traffic is going beyond your dimension, whether it's legitimate traffic, in which case you grow your VNFs, or it's attack traffic. Right. So that would be more along the lines of an anomaly. Does whatever you did, can it predict those type of anomalies? So that's the first question, and I have a second follow-up as well.
Right, so the first one, like the way I explained it, is probably a mischaracterization or misled you into thinking that it's only looking at weekends and so on and so forth, or like anticipatory traffic. It is looking at surge traffic, because some of these services are things like Slack, where they do not know like if there are going to be more people signing up and then using the service, or there might be like just more usage because of something else happening, like because maybe the Amazon infrastructure is down, and that everyone who's using who's on Slack and has ops might just like get onto a lot more calls because there's something happening somewhere else, which is causing them to communicate more. So yeah, so that's like that's where most of our anomaly detection. And what I talked about is also RTT, which is more like consumable by the audience. What we're doing is like we were looking at 300 or 400 features on a call. So the devices, the cameras, the mix of Wi-Fi chipsets, the 3G chipsets, the network operator, the ASs. We're looking at all the throughput, like all the network characteristics, like throughput, jitter, RTT. We're looking at like what type of burst loss characterizations we have, and so on and so forth, which helps us like figure out if these things are actually what you talked about. Is it just like a small outage, or is it like something that happens more predictably so that we can predict?
I mean, this is much harder to do than people typically realize. Another aspect to this is that when you create time series and you analyze them and you have space exploration of when traffic dips on the weekend and when it doesn't, many times you get a lot of false positives. But anyway, this is all.
So one of the things with that, what we've noticed is that you actually need like, I think 400 weeks of data to get that right.
Even with that,
that's almost 10 years. So, and we are only year 4. So.
But what was true 10 years ago is not necessarily true now. Right. So you need more recency rather than go 10 years. And the other last question, I know we are wrapping up. What type of algorithms did you use for anomaly detections?
So, like, this is firstly multi-agent. So one of the things that we try to do is build notifications, which would be linear algebra or similar, and then actually take notifications and try to apply AI on that. So it's like LSTM and CNNs to figure that out. So in some cases, we're taking recency into account to figure out, and that's why the time span. So we basically have lots of data aggregated over different windows so that we can actually look at some of the things that you like basically said, like you can get it wrong, and that's why we have all these cascaded time windows that we aggregate over so that we have like some kind of check and balances to make sure that we have both recency and like old data. Because if you train an AI, you have to either like remove all the old data and just remember the anomalies, or you're only looking for recency. So we have all these algorithms that work in parallel with each other, and then something takes that, and that's why we call it multi-agent. And there's an AI that runs behind that to like take all this input to figure out what's interesting. And this also plays an important role for us because we give this, at the end we have the human element to guide some of the input when we are showing it to them. And there are multiple people, it's not just one person. So if there are multiple people logged into the same account, we're also looking at who's looking at what. Like maybe like all of them press, don't show me this, then we know that this is not interesting. But maybe like the product manager clicks it and not the operational, right? So we can learn from that as well, like who's consuming what notification and what's important for them. And then learn across that. And that's actually different from before because I think a lot of the network management.
Sorry, we're going to have to, we have another talk coming up. So thank you very much. I'm sure Varun will be around.
Thank you.